So for this question, it says, show that the pair Rn with the distance matrix infinity, L infinity in example 1.9 is indeed a metric space. So for example 1.19, this is where it defines the L infinity metric right here, which is the supremum of the corresponding pairs with the same index as such, right? I think it's very important to consider that this is only for the supremum of the corresponding pairs, not just for any pair of elements that have different indexes, but only for pairs that have the same index right here. I think this is a pretty good definition of supremum and infimum that clearly shows what it means to have a least upper bound and a greatest lower bound. And that's also reminded of the four axioms of the metric space as such right here. So for axiom A, it's pretty simple because as we see it, we basically just get a set of all zeros, the supremum of the set of all zeros, which is obviously going to be zero trivially. For axiom B, we're going to do a very similar contradiction that I've been doing for the rest of these metric spaces. And we can clearly see that if this is equal to 0, that implies that every single one of these has to equal 0, which implies that they're all equal to themselves. Because as you think about it, right, it's an absolute value, so the lowest value is 0, right? And so therefore that's a contradiction right here. For axiom C, it's pretty simple. We can clearly just manipulate it. It's an absolute value, and it's basically the same thing right here. Axiom D is a little more complicated. So this is where we define all the stuffs, and I'm going to find some optimization aspects for X and Z right here, such that these are the optimization things. No, sorry, this is the maximum pair displacement or pair difference right here. But I'm going to define yx and yz max right here, such that for x and y sets, this is the max displacement, and y and z, this is the max displacement too right here. I'm just going to say like y naught is just going to be the set like right here. And so we're basically going to plug this in like right here and get this. This is just the definition of just plugging it in. This is the maximum value right here. I'm going to plug in this y naught right here from the set y. And we basically say, so using triangle inequality right here, we can split this up like right here. We can then use, so this is really important, we can then use the idea that this is the supremum, right? So any values in here have to be less than or equal to the maximum value of this set, because this is defined as the supremum of x and y and z. Therefore, that is equal to this, and therefore this is shown to be true.